Strong from the Encyclopedia team. It is with great honor we have Dr. Massimo Palma for this interview. Thank you very much for coming.
Thanks to you, for this opportunity of this interview.
So, Dr. Palma, please tell us a little bit about yourself.
I'm the head of the Physics and Chemistry Department of the University of Palermo in southern Italy, and we are based in Sicily. I've been working on quantum information processing and quantum computation since the early stage, since the early 90s. And so I've seen the development of this research field, the quantum technologies over the year, and just changed a lot and has taken different forms, some of which were possibly even unexpected in the early days, in the early 90s. And now my group is active on different research lines. We're working on a new form of quantum computation and quantum algorithm, on open quantum system dynamics, on quantum optics, and atomic and optical physics, and with particular reference to the applications and the implications for quantum technologies.
So could you please provide a little bit more background on your research topic, quantum technologies?
Okay, quantum technologies is now what we call quantum technologies. It started in the 80s and 90s. In the 80s, people like Richard Feynman, Charlie Bennett were interested in different aspects of the interconnection between physics and computation, in particular the thermodynamics of computation. And soon it was clear that quantum effects had to be taken into account in the description of computational process. And therefore, it started this interest for quantum computation. However, at that time, the interest was restricted to a rather small community. High-profile scientists, but very small community. What changed perspective and the interest for the physicist community towards these kind of problems was the discovery of the Eckert 91 quantum cryptographic protocol on the one hand, and in parallel of the work by David Deutsch on quantum computers, on quantum Turing machines, and quantum gate implementations of quantum computing device. And this was in the early 90s. The Eckert 91 quantum cryptographic protocol, which was discovered by Arthur Eckert, was published in a physics journal. It was not published in like most of the previous work in the conference proceedings. And was published in Physics Red Letters, and this brought to the general interest, brought to general audience, general readership, the attention towards, the applications of quantum mechanics to that stage communication physics. As a side effect, people started looking at quantum computation. Again, the interest was because quantum computer could, the performance of quantum computers, of quantum algorithms was very much linked with cryptography. In particular, there was the discovery of the Shor algorithm, which showed how to factor efficiently large numbers, and which again had strong implications for quantum cryptographic applications. They again brought to people started to believe there was something in quantum computation. And for a long time, for something like 10 years, quantum technology basically meant quantum cryptography on the one hand, quantum communication in a broader sense, and on the other hand, quantum computation. People started looking on the one hand, try to understand the class of algorithms which were implementable on a quantum computer. On the other hand, people started to look at the hardware. How would you build a quantum computer? How would you build a quantum gate? And things like this. And so experimentally started to look at these kind of problems. But as time went on, people started to realize that not just quantum computation and quantum information transmission and cryptography were subject in which areas of research in which quantum effect could be beneficial, could give some extra kick, could be an extra resource. But people started looking at quantum sensing, for instance, and quantum metrology. So the people started to realize that there is a broad area of topics, broad areas of research in which quantum effects could give an extra ingredient, could open an avenue, could open new perspectives, which were prevented, which were not possible if you set yourself to a classical physics scenario. So this is roughly the evolution of quantum technologies. Now, in most Western countries, there are large-scale projects to fund all the various research lines which fall under the broad umbrella of quantum technologies. In Europe, for instance, there was this big European project which is called Quantum Flagship. Similar projects have been going on in China, which have been actively working in quantum communication and like quantum satellites or quantum internet. There are several quantum internet projects, one going on in China on satellites. The similar project is going on, is being financed and is underway in Europe. And at the same time, the US has been heavily investing, especially private companies. Now also private companies are interested in this research field, which is not just, has left the, if you like, the stage of basic research going more and more towards real applied research. I mean, now there are quantum computers working, I mean, imperfect, noisy, far from the ideal quantum computer on which you can implement error correction, this limit, but still you have devices which can implement small routines, and companies like IBM, Google, or Amazon are investing heavily in this research. So it's a rather exciting and promising research area.
I'm sure algorithm goes out to every way of life. So what makes you want to research quantum technologies? Did you get any influence from other people in the first place?
I think that quantum technologies are typically something I always tell my students. For people working in physics, I mean, up to a relatively recent time, the frontiers was particle physics, or if you like, astrophysics or cosmology, and people doing research in other aspects of physics were considered like a lower grade kind of research. I mean, the interest for quantum technologies brought of central interest as fundamental research, quantum technologies, quantum information processing. And so, I mean, it is important that, and of course, they have been strongly influenced by my colleagues, especially, I mean, the Oxford team, like Arthur Eckert, David Deutsch, with whom I've been working in the early stage. And at that time, we were very few people, but Anton Zeilinger, for instance, we were very few people who had altogether a strong interest for these aspects of science, which looked exotic, but which had a strong impact that changed perspective on the way you look quantum mechanics and physics itself.
Thank you. So what is the interesting part about your research?
Now going to my specific research, I mean, I've been gradually moving from, and I'm still working on the borderline between quantum optics and quantum information theory and open system dynamics. But over time, this has changed perspective. So far, we've been looking at how quantum noise impacts quantum computation. Now we are going towards a direction in which we're looking at complex quantum systems with many body systems, or anyway, a system consists of strongly interacting subunits as a new way in which you can, a new hardware which allows you to perform quantum computation. So a change of perspective from looking open system dynamics as something which you should prevent in order to have coherent quantum computation algorithm, to a perspective in which you use the complex quantum system itself to perform a new form of quantum algorithms. And of course, we are also looking at the way in which you can engineer. In my group, there are people working on how you can engineer topological materials or non-emission dynamics, which means a particular kind of exotic states of matter, which you can engineer in quantum optical devices. And so these are the main research areas my team is working on at the moment.
So when you are developing something, what are the challenges that you are facing?
I mean, in this particular situation, I'm talking about the challenges my team and my university is facing. Okay, we are a rather large group working, however, in Southern Europe. Okay, and Southern European countries have a less prosperous, I mean, economic background. I mean, have underprivileged regions within the UK. So you have to fight in a way to, on the one hand, to find fundings, on the other hand, to find appropriate to maintain a large number of international links. We've been rather successful in keeping international links. It's unthinkable now that your own group does its own research without being without putting yourself in an international framework. We've been rather successful in doing this, in spite of the general difficulties. The pandemic, of course, has made more difficult to maintain international relations. However, I mean, over the past couple of years, we still managed, in a way or another, to broaden our set of international collaborations. I mean, I think, on the whole, I think we have been performing rather well.
I'm glad to hear that international collaboration has been flourishing, and I sure hope you guys will get more funding very soon. So, what's your prospection of this research field? Is there any next move from you?
Okay, at the moment we are trying to understand which direction to go. I mean, again, given specifically our team has grown very much in size and we have different kind of new expertise, we have decided to go, we're actually going towards more different directions and to broaden our range of research. And again, to predict completely what next move will be with certainty is difficult. However, I mean, fields like quantum thermodynamics, neuromorphic quantum computation, like quantum neural networks on the one hand, and quantum reservoir computing, and on the other hand, new metamaterials like topological materials seems to be promising avenues, and which will benefit strongly with collaboration with teams with different expertise and different background. So it is the strong interdisciplinary nature of this research which is the key ingredient which is driving us towards our new research lines.
Thank you. So, Dr. Palma, before we finish, is there any acknowledgement you would like to make?
I would say my students. There is a saying which is actually apparently was said by Galileo Galilei, which says in Italian it runs "Triste quel discepolo che non avanza il suo maestro," which in English sounds "Poor is the pupil that does not surpass his master." In my viewpoint, is poor is the master who is not surpassed by his students. So, I mean, students are the future of research. Some of my past students are very successful researchers now. They are themselves head of departments or leading good research teams. And I'm working hard to make sure that my new students, my current students, will have an exciting and successful research activity, I mean, in the future. And so, I mean, people I really would like to acknowledge for what I'm doing is basically my students.
We wish you and your students the best of luck for your future endeavors and research. Thank you again for joining us, Dr. Palma.
Thank you for the interview. Bye.